Hello, everyone. It's been so long since I have met you all. Thank you for having come here today. It's been 20 so far. I think it's quite good number to begin with. So uh, today I want you to type your questions if you have any in the comment box. Then you can ask when it is your turn. So it is always going to be the same way. Those who have questions can type your question in the comment box. So you know the order of the questions that you have typed. And based on that order, you can raise your hands. And the co-host here, Mr. Subhash, will also make you as a co-host so that you can unmute yourself and ask your questions. So that's how it is going to be. So as I said in my email, there is no technical session today because it's been so long that I understood most of you could have a lot of queries, doubts, and also clarifications you may need to ask. So I skipped the technical session today. And I would also like to make this meeting recurrent every month instead of every every once in 4 months. So it would be easier for me to accommodate all of your requests too. In this span of 4 or 6 months since we met last time, there have been so many emails from all of you, and I honestly don't remember most of your queries because it has been so long. So I would really appreciate if some of you are there, you can ask me again, and I'll try always my best, as I do always, to give you the clarification you need. Yeah, with that, let's begin. So whoever who has question now can raise your hands, and Mr. Subhash will make you to be a co-host, so you can ask your question. Yes, Dr. Dhanasekaran.
Yeah, good evening to all.
Yes.
Yeah, my
Good.
how we can fix the potential for HEF, particularly in the acidic medium, acidic conditions. But generally, alkaline we can fix for OER, we can fix 0 to 0.8 up to as our wish. For HER in alkaline medium, minus 0.2 minus up to 1.5. But I have little bit doubt in the acidic condition how we can fix in the for HER particular.
Yes.
And OER also.
Okay. Actually, it's very easy. All that you need to do is follow the Nernst equation to convert your potential into reversible hydrogen electrode, right?
Sure.
So you know
Yes.
the reversible potential for hydrogen evolution reaction and oxygen evolution reaction versus RHE are 0.0 volt for HER and 1.23 volt for OER, right?
Sure.
So
Yes.
only variable you have here in this case is that you have switched the pH from 14 to 0.
Yes.
So in the Nernst equation, which is the, I'm typing it in the comment box so you can see. Somebody wants to enter, I couldn't type. Yes. Dr. Dhanasekaran, do you see the equation?
Yeah. Yes, I
Yes.
saw that.
So,
Yes.
yes. So this is the equation we always use for
Yes.
converting the potential
Yes,
into.
this is common. We have to, RH conversion.
Yes. So the potential window you told for alkaline medium is based on the calculation that we get from using this equation, right? So in this
Yes.
case, you need to substitute 0 or 1 as the pH, depending on the concentration of the acid you are using.
Sure.
So it is usually, if it is going to be 1 molar HCl or zero point 0.5 molar H2SO4, the pH theoretical calculation of pH will give you 0 as the pH. But
Sure.
if you perform platinum stripping voltammetry, it will show you around 700 millivolt, minus 700 millivolt against Hg2SO4 reference electrode, MMS reference electrode. The standard potential of the MMS electrode is 649. 640 to 649, depending on the electrolyte you fill inside the electrode's chamber. So, in any case, if you are using an MMS electrode as a reference electrode for acidic HER and OER, for HER, you should choose a potential at least 200 to 300 millivolt before the onset of HER on the surface of PT, which means that you should choose a potential somewhere around minus 0.45 to minus zero point 0.5, and you can fix the in potential value or the vertex potential value depending on your preference, your own preference. You might want to polarize the electrode up to 1 volt, or you may also want to restrict below 1 volt depending on the activity of your material. If it is too active, obviously the current is going to be higher, and your electrochemical workstation may not be able to sense the higher current density your catalyst may drive. So in that case, you can limit the vertex potential depending on the material and the activity of your material you are using. So it is for HER, it should be somewhere starting somewhere around minus zero point 0.5. So if you are using a non-PT material. So if you are using a PT material, it is always wise to start from 0 volt against MMS, because there will be platinum oxidation and reduction peak, which will also influence the hydrogen under potential deposition and also hydrogen desorption peaks. These two phenomena have huge influence on the HER activity of platinum-based material. Yes.
One more question.
Yeah.
You mentioned PT-based material means that is counter electrode or in working electrode?
No, working electrode. If you are using a PT-based catalyst, this day you can see people are decorating PT nanoparticle, doping PT atoms into some other catalyst, and also they are using PT single atom catalyst. In those cases, it is always wise to start from 0 volt and polarize it up to minus 1.2 per se. So you can get the HER, hydrogen under potential deposition, and if you are performing CV, you will also be able to see hydrogen desorption peaks, which you can use for the calculation of electrochemical surface area. So this is for the case of platinum containing working electrodes. Okay, if your material is not containing any platinum or ruthenium or iridium, it is made of non-noble metals. So you don't have to, you shouldn't polarize it beyond minus 0.4, because beyond minus 0.4, the potential against the reversible hydrogen electrode scale is anodic enough in order to affect dissolution of your non-noble metal oxide catalyst. So when you are using a non-noble metal oxide metal-based catalyst, could be chalcogenide or phosphide, anything, always try to limit your potential, anodic vertex potential closer to minus 0.5 against MMS reference electrode.
Okay, yes. And that this reference electrode, many reference electrode is there for silver chloroelectrode, HgO, and some of other reference electrodes also. So can we, for acidic medium, silver, can we use silver chloride?
No, definitely not, because silver chloride and colloidal electrodes, they are actually made to perform well in the pH range of 6 to 11. So these are the pH range in which the standard potential of these two reference electrodes were experimentally proven to be unaffected even after prolonged use. I'll give you two pictures. So when you use an AgCl reference electrode in an acidic solution, the very first thing that you are going to be seeing is the a difference in the standard electrode potential of your reference electrode, because the reference electrode, AgCl reference electrode compartment, is filled with either 1 molar KCl or saturated KCl. Sure. But the solution inside your electrochemical cell is going to be different. For example, 0.5 molar H2SO4. So in that case, you have two different anions, and also
Sure.
even though the charge and the cations are the same, they are different in terms of their ionic radii. So when these differences occur at the interjunction, I mean at where the frit of your reference electrode meets the electrolyte solution, there will be a small liquid junction potential generation. This liquid junction
Um,
potential generation tend to vary as you expose the reference electrode more and more to a different electrolyte containing different anion and cation. And beyond that, you also know the pH of 1 molar KCl or saturated KCl inside the reference electrode chamber is closer to 7, but the electrolyte's pH is 0. So you have a big pH gap between the reference electrode chamber and the electrolyte chamber. So when there is a pH gradient, so we know that there occurs migration of ions to affect the neutralization reaction. When this occurs, the concentration inside the reference electrode chamber keeps on changing, which will also affect the potential of your reference electrode. So because of these reasons, you should never use AgHCl or Calomel electrode in acidic condition.
so better to, so as your suggestion, based on HgHO is the best, right?
No, HgSO4. If you are
So
HG,
HgHO also we cannot use, right?
no,
Okay.
that's what I'm trying to say. Yes,
Okay.
HgHO. Yes, HgHO is specifically for alkaline medium because HO is too
Okay.
stable, highly stable in highly alkaline solution. So it is a
Sure.
better reference electrode.
So
Similar,
another, apart from sulfate, mercury sulfate, can we use any other reference electrode like a
copper,
carbon cloth?
No, you can use copper sulfate.
Okay. Okay.
Yes, if you are afraid of using mercury, you can always use copper sulfate. But the problem with copper sulfate is that it will not give you a long-lasting life. The copper inside the copper sulfate solution will corrode very easily.
Okay. Yeah. Sure. Sure.
Yes. Yes.
Okay. Recently, I found in alkaline medium, I was used reference electrode as counter electrode as a graphite rod electrode in alkaline medium.
For
Okay.
which reaction?
For OER.
Okay.
I used platinum as a counter electrode, graphite rod as a counter electrode, mercury oxide as reference electrode, and my material. But after some times, that electrolyte, it will color change to happen. I don't know why.
Yeah. Yes, it's because of carbon corrosion.
So it is
So
normal that color
yes.
anything affect the over potential.
Yes. That's usually normal, but once the carbon corrosion occurs, that also pollute the electrolyte with smaller carbon species. Small, I mean C1 to C3 species. These species can influence your OER activity significantly depending on the concentration. So when you want to use graphite rod as a counter electrode for OER reaction, you should be very careful that the potential of the graphite electrode is not polarized beyond 0.8 volt against RHC at any condition. What people usually do, which is a mistake here, is that they will use graphite electrode as a counter electrode, but when they want to perform cyclic stability for the OER catalyst, they will set 0 to 1 or 0 to 0.8 in the potential window. When the working electrode potential reaches 0 volt, the counter electrode potential is adjusted in such a way that it will go beyond the carbon corrosion potential in the anodic side. So that is when you see the color change. So when you are using,
in my cases, I was used up to 0 to 0.8 only. Even I did HER also. Even HER also that color changes happen.
Yes. When you, when you perform HER with your working electrode, your graphite electrode basically does the OER reaction where carbon corrosion is inevitable. So when you are using a carbon-based counter electrode, the color change is basically highly anticipated. So it becomes vigorous depending on the potential, the vertex potential up to which you are polarizing your electrode.
Okay.
So
But
Yeah.
Sir,
So
but many of the papers they are reported and using a graphite rod as a counter electrode. Suppose I
yes,
don't know, they meet these changes. Suppose they met this
yes,
changes.
we all did. I did, and my seniors did, and also my juniors, whoever is currently working on this area, they are also experiencing this thing. And when we want to polarize to a larger potential, we simply change the counter electrode. So if it is the reaction of our interest is HER, we use IR plate or ruthenium plate as the counter electrode. If it is OER, we will use platinum foil as the counter electrode. So in
Yes,
that
what is
case,
the yes, 1 minute. What is the problem? Means recently I uploaded a paper in
okay,
ACS that reviewer asking for
mm,
suppose to you are using platinum at a
mm,
counter electrode as a counter electrode, it may
mm,
deposit on your material so that lower potential you achieved. Like that
yes,
assumption they actually
yes.
sent to us.
Actually, it is not assumption. It is experimentally proven, and there is a paper in I think ACS Energy Letters. Uh, Actually, when we study HER in no circumstances we should use platinum as the counter electrode, because the platinum dissolution and redeposition on the working electrode is a proven phenomena. So when you are studying HER, never use platinum as the counter electrode, but you can always use iridium plate or ruthenium plate. Their corrosion rate of corrosion is much less than
Mhm.
the corrosion of platinum.
Okay,
Yeah,
okay, okay.
but so to avoid this issue, if you use graphite rod, there will be carbon corrosion, and the carbon corrosion always pollutes your solution, and that will also affect your activity later.
Okay. So
Yes,
this color changes surely happen, means happen
yes,
and it is reduced, I mean affect our potential, right?
yes, yes. After a while, it should affect.
Okay, okay, okay. Thank you.
If you are not comfortable with using either platinum or graphite rod, you can always use freshly etched titanium as your counter electrode, regardless of
Okay,
OER or HER, because titanium corrosion in alkaline condition is nearly impossible. So it won't give you any issue. Moreover, titanium is a poorly active material for both OER and HER. In that case, you will not have any influence from uh,
okay,
any dissolution that may occur with titanium. So if
okay.
you have a
So
titanium mesh or file, you can use that as a counter electrode.
okay, so in the carbon material, we can use carbon cloth. I think it is not happened anything.
No, carbon cloth will withstand more than your graphite rod, because the carbon cloths what we get in our laboratory are usually coming with the PTFE coating. So as long as the PTFE coating is there on the carbon cloth or carbon fiber paper, you will not see any carbon corrosion. But once
Hmm.
the PTFE coating peels
Yeah,
off,
leaching.
then,
Yeah, yeah.
then color changes occur.
Okay, okay.
Yes, yes.
Thank you. Thank you.
Yeah. Yes, Mahesh Falek. I don't know how I'm pronouncing it correctly. Good evening, sir. I'm working on HROR. I'm making catalyst using cobalt and borate. The electric acid shows less activity after 2 to 4 days. What are the reasons for this degradation? To help you with this clarification, I need some more information. So, what is the catalyst you are preparing? Is it cobalt borate or boride? Mr. Mahesh, are you there?
So it is cobalt boride, sir.
The cobalt boride. So, have you used any physical or chemical vapor deposition method or the chemical reduction method?
Chemical reduction method.
You used borohydride and cobalt salt, right? Yeah, right?
Yes, sir. Yes, correct. Yes, yes, right.
Yes. Yeah. Yes. So, this method will give you cobalt boride, but the proportion of cobalt boride to borate is very, very, very less. And moreover, when we synthesize cobalt boride, after a few days, the hydrolysis of boride to cobalt hydroxide and boric acid is almost spontaneous. So when you don't have your synthesized catalyst after 2 to 4 days, it is common to see such activity loss, because there is no more cobalt boride. Your cobalt boride has hydrolyzed. Even this hydrolysis can occur with moisture in the air, And it even occurs with atmospheric oxygen, because cobalt boride is not a stable catalyst. I hope I answered that. Yes, Mr. Abhishek Rai, if you are a host,
Yeah,
you can. Yeah.
yeah, sir, I
Mahesh,
have a question. Hello?
just a minute. Yeah, Mr. Abhishek, just a minute. Mr. Mahesh, if you have something to ask, you can. Yeah.
Sir, continuing with the same question, if I keep my
Yes. Yes.
material in ethanol, then also it is showing the same effect.
Yes, it should. If you have kept your material in vacuum, where the possibility of hydrolysis, even the oxygen, atmospheric oxygen promoted hydrolysis is very less, your material should retain the very less proportion, whatever you may have after your synthesis, of cobalt boride, should give you the same activity or very similar activity. So please try storing your material in a vacuum chamber. So it must help you to realize the same activity even after a week or so. I did realize such a change with one of my earlier studies where I was working when I was working with nickel boride. So I noticed the same thing. So when I use the vacuum chamber to keep my samples, I was able to reproduce the activity, not exactly the same, but very close with 90 to 95% similarity, even after 15 days. So that might help you.
Sir, can we convert these materials into more stable materials?
Yes, you can think of forbidding all the possibilities that can lead to hydrolysis and atmospheric oxygen promoted hydrolysis. So the best way, as I said, is keeping it in vacuum. The second best way is coating it with the hydrophobic resin, such as PTFE. So but that is not a very common process, since we are all material chemists or physicists who work on creating interesting materials, and we don't want to have anything that is sticking on the surface of material. So if you want to work with cobalt boride, I would suggest you two things. So always prepare your catalyst freshly, or keep your catalyst in the vacuum chamber. So currently, I cannot think of a different strategy which will help you.
Sir, there is one more observation.
Yes.
Is that when I keep the catalyst while loading the catalyst, I am making a ink. Okay, so I am mixing that amorphous powder in ethanol.
Okay.
So if I keep my sample in ethanol only, it will remain for longer time.
Yes.
Active remain for longer time.
There is a possibility for that, but if you see, even the purest form of ethanol comes with 0.1% water, because removing all the water from ethanol is impossible. So that water can do some damage. So if you are interested in protecting in such a way, you may try using acetonitrile or THF instead of ethanol.
Okay, sir. Thank you.
Yes. Yeah, that's a good thing. Yes, Mr. Abhishek Rai, please.
Yeah. Sir, I am working on supercapacitors and oxygen evolution over here. So here I have found that with increasing the scan rate for a particular electrode material, the peak-to-peak separation, the cathodic and anodic portion is increases. That with increasing the scan rate, the anodic peak is shifted to more right, and cathodic peak is shifted to the more left. I want to know that why is this occurring actually?
Yes, I think you have attended all my earlier sessions, so you should know this, because
Yeah,
this is
that is due to diffusion, but I'm how diffusion is actually affecting here. I'm not clearly understand.
yes. So in the case of modified electrodes, it is not like the sensors where people study about the reversibility of freely diffusing or surface absorbed, specifically absorbed analyte. So in modified electrodes, it is almost the same, but the thing is that here it is thin layer diffusion. So we say it, thin layer diffusion. It is the diffusion of the electrolyte into the catalyst layer. Okay. So we know from our earlier discussion that from the scan rate effect and monitoring the peak-to-peak separation, we can actually predict the nature of the process, what we are seeing, the redox process. So as you said, the peak-to-peak separation increases with the scan rate. It could be because of two things. The very first thing is fundamental thing. When the scan rate increases, the IR drop increases. So naturally, the interface feels the potential what we intend to apply after a certain time. So since the scan rate is very high, is kept on increase. So obviously there will be a peak shift. The second reason is that your reaction, I mean the redox reaction, what you are monitoring for supercapacitor or OER could be quasi-reversible reaction.
Yeah,
So,
quasi-reversal. Yeah.
yes, these are the two reasons. Yes.
So I want to know that with quasi-reversible process, how it's affecting the diffusion process. Uh, uh, I mean, the reaction is quasi-reversible, but with the diffusion,
Yeah. Quasi-reversible reaction does not affect diffusion. The problem is that when your reaction is quasi-reversible, for example, say you have 100% species consisting of A, so which is being oxidized to B. Okay, so when you come back, the B is supposed to be reduced back to A 100%. It is the case of a reversible reaction. But in the case of a quasi-reversible reaction, some portion of the oxidized B stays as B itself. So those oxidized B, which is reluctant to be reduced, will influence the amount of A that is to be oxidized in the next cycle. So this is how it may affect, but there is no direct in the case of thin layer diffusion where we use modified electrodes. But in the case of sensing and analyte, like people are the sensor people, so there is totally a different definition that is solely depending on the structure and the nature of interaction of the analyte with the electrode surface.
Okay.
Yeah. Since your case is a modified electrode for supercapacitor and OER, it is purely a phenomenon of thin layer diffusion.
Okay. And another recently we are performing OER using AgCl as a reference electrode and sometimes as a AgHgO as a reference electrode in alkaline medium. So what I think that I actually observed that with AgCl has a different over potential, whereas in case of AgHgO is a completely different over potential. But why it is happening that the reference electrode should not be any effect on the over potential?
Yes,
We
because
actually short the AgHgO and AgCl. It's a completely have a voltage gap between the two electrodes.
yes,
So
once you converted the potential to RHE scale, the reference electrode should not have any influence on the over potential. The problem is you should not use AgCl in alkaline medium. First thing, for the same reasons I have said to Dr. Dhanasekaran. Secondly, I want to know, have you calibrated the reference electrodes?
Yeah. In for both the AgHgO and AgCl we have calibrated. Firstly, we have used the PET modified AgCl electrode,
So
and for AgHgO is also.
Yes, may I know how did you calibrate your reference electrode?
We have used the 1 molar Kevit solution for AgHgO,
Okay.
and for particular pH we have calibrated.
I want to know how did you perform the calibration? So what method did you use? Yeah, what method did you use to calibrate?
Normal, just pH corrections. 1 molar K.
Yeah. So that won't help you. So please try this thing. What I'm going to say now. So regardless of the reference electrode potential, whatever you are using, so even though it is said to be the same, no, most of the people, those who have been working with electrochemistry, never calibrate their reference electrode, because they assume if it is AgCl, it is going to be 197. If it is colomol electrode, it is 232. If it is HCHO, it is going to be 98 millivolt. This is something which is commonly done by the researchers in this field. But believe me, The same reference electrode can have different potential value every time you change the solution inside it, because it
Okay.
has to do something with the equilibration with the electrolyte in the electrochemical cell, and also the minute pH changes that occurs because we make the solution. So there is a high possibility for making human errors. So when the error is very high, the potential obviously changes. So what I usually follow to avoid all this issue that, yeah,
We are
so
using
you
the ferrocyanide solution that time to measure the voltage of AGHGO. We found firstly 190 to AGHGO electrode and then complete the measurements. And for AGHG cell is a 230 and complete the
uh,
measurement. That's the work for.
yes, that is one way, but there is an easiest way, which is using platinum as a working electrode, and your reference electrode, the potential of which is to be determined, and a solution of precisely known pH, okay, and a
Yes.
counter electrode of your choice. Okay, so when you have platinum as your working electrode and the reference electrode, whatever you have in your hand, for which you want to determine the reference electrode potential, you can perform cathodic polarization and see at which potential platinum surface is giving you HER onset. Okay,
Okay.
yes, and you also know this equation which I have just typed in the comment box, which we usually use for RHE conversion, right?
Yeah. Yeah.
So in this case, the unknown factor here is the reference electrode potential. You
Yeah.
know, the potential of platinum's HER onset is 0 volt. So ERHE is obviously 0. And you know the potential, I mean the cell potential of your experiment. And you keep E reference as X, and you know the pH. So solve this equation, you will get your reference electrode potential accurately. This is the best way one can get their reference electrode potential uh, with the highest precision possible.
Okay.
So if you use
Okay.
this potential after doing the calibration like this, you will not get that issue.
Oh.
Uh,
Okay. Okay.
yes, yes,
Mm.
please try this. All that
Okay.
you need is you need to have a platinum working electrode,
Okay.
and
Okay.
make sure that the platinum surface is free of platinum oxide.
Okay.
Yes.
Okay. Thanks.
Always
Thanks.
perform, yeah, always perform 25 CVs at least, and take the onset potential of the 25th cycle. That is the most accurate. That will be more accurate. Yes, I don't know the superlative of accuracy. Yeah. Okay. Yeah. Thank you. I hope that
Thank you.
helped you. Yeah. Yes.
Thanks.
Yes.
Thanks.
Yes. Yes, Bharat Bhushan, IIT Kanpur. I want to understand the fitting of EAS model to EAS data. I find that there is no uniqueness to the equivalent circuit fitting. Yes, and there is no uniqueness. And if you ask me, I will say there is no big of a use of fitting these circuits, because you can get everything that you may get by fitting your circuit. I mean, Nikos plot with the EEC circuits or Randall circuit, just by plotting the other two plots, Bode impedance plot, I mean Bode absolute impedance plot, and Bode phase angle plot, and of course your Nikos plot. These three plots can give you all the information that you may get from fitting. But I would say fitting is not an ideal practice, because fitting is actually done by a software which performs number of iteration and tells you that this model fits your circuit. But this could be entirely wrong. This could be entirely wrong. For the same Nikos plot, I can come up with 2-3 EEC fits, so, which means that the software will give you just the guess, but it is not the ideal result. So I never use Rendell circuit, nor recommend the use of the same two others. So if you are worried more about the ES fitting, I would suggest you to watch the lecture. I actually forget. I'll email you. There is a lecture in YouTube. He's a famous electrochemist from Norway. He has given, and at the end of the video, he also said that performing EEC fitting is a meaningless thing. So I believe that. So if you are interested, you can watch that video. Yes. Yes. Yeah.
Thank you, sir, for this very nice explanation about ES. I have
Yeah.
one more question that so what information we can get from this uh, uh, Bode phase angle plot? Let's say that we get a hump or we get a peak in Bode phase angle. That is a
Yes.
phase shift
Yes.
with respect to frequency.
Yes.
So
Yes. That's right. Yeah.
let's take the example of two cases. In
Mm.
case the peak value is at lower frequency and in other case the peak value is at higher frequency.
Mm.
How does this system behaves, or what is the electrochemistry behind it
Yes.
that is happening inside the
Yeah. Yeah.
solution?
Yes, that's a very good question. So let me first explain what we get and what we infer from Bode phase angle plot. Like you
Yeah.
said, it's a phase shift, right? So basically, the y-axis is with the units of degree. So this is the phase shift between the potential and the electrical,
Current.
yeah, the electrical elements, right? So for a resistor, so we know that in all AC circuit, there are three main elements that impede the flow of current. So first one is resistor, and then capacitor, and then inductor, right? So in resistor, where there is only resistor, which means that the circuit is basically a DC circuit, there is basically no shift between the voltage and the current. They are in the same phase. Their magnitude may be different, which means that in your Bode phase angle plot, if your phase angle is closer to zero, yours it tells you that your system is controlled more by the charge transfer, and it behaves more like a resistor. If it is exactly 45, so it is a diffusion control process. So we know from Nyquist plot that a Warburg component with an angle of 45 degree indicates the diffusion control process. And if it is more than 45 degree, we say that it is capacitive, more capacitive in nature. The impedance comes from capacitance. Much of the impedance what we experience in our circuit comes from the capacitance. So this is what we take. This is the first information. The second information is the place, I mean the frequency at which we see the peak. Okay. Yes. So when the frequency is very high, it means that your interface does not take up more time to affect electron transfer across the interface. So we call it the RC time constant. Okay. So the time required to charge the capacitor element in the AC circuit through the resistor up to 63.2% of its total capacitance. This value is mathematically derived, and so this is the threshold for any capacitor to allow the charge transfer across the interface. Okay, so the time taken by the interface to charge its capacitor up to this point so that there can be successful charge transfer across the interface is called the RC time constant. So if your peak occurs at a very high frequency, which means that the capacitor has been is charged quickly, so your electrodes or interface has begun the charge transfer process immediately. So if you are observing your peak at a very low frequency, it means that your capacitor is taking up more time, or this is the reason when the surface area or the electrochemical surface area of the material is very high, as if the material is porous, or the double air capacitance. If double air is large, the capacitance is usually high. So charging the capacitor up to 63.2% of its total capacitance takes up time. So after that time, only you will be able to see the real charge transfer, I mean electron transfer. So if you are seeing both for the same impedance, it is the indication of two distinct electron transfer process occurring at the same interface.
Oh, that means at high frequency and low frequency, if I am seeing two time constants, then
Yes.
they are associated with two different electron transfer processes. And sir, one more question.
Please understand, not two different, two distinct, I said. So which means that it can be of the same reaction happening at two different rates.
Okay.
Yes.
So
Yes.
I have one similar question that so once I imagine at my table there, what is EDL exactly is? There are 3 to 4 models, I think, Stan-Gary model to define EDL, and another is there are 2 or 3 models. I am not able to recall, but on a large, if I want to capture your imagination about it, how would you
Uh,
enlighten us about this EDL?
yeah, electrochemical double layer. There are actually not just three. There are actually nine methods, I think, and nine models, I think.
Yes.
So, electrochemical double layer is actually proposed first by we all know the very famous double layer method. We see Helmholtz, yeah, and then there came Guy, and then Stern model, and all this model has its own advantages, merits, and demerits. The very first thing Helmholtz and Perrin model showed us was that it is very similar to the parallel plate condenser that we study in physics, plus two physics. So, when we have two conductor separated by an insulator, charge accumulation occurs opposite with opposite signs. So that is what we call parallel plate condenser. So Helmholtz and Perrin model showed us that postulated that the similar construction of a rigid double layer is occurring on the surface of the electrode. The surface of the electrode can either be charged positively or negatively. So depending on that, oppositely charged ion will come and stick firmly. So this is very important, firmly. So it is not a loose layer. So it is just like the parallel plate condenser. And they also predicted that the capacitance of this double layer, electrochemical double layer, is constant, and it won't change depending on the distance or the potential. But it was later proven to be wrong experimentally. So it needed some modification. The postulates of Helmholtz and Perrin model needed some modifications. So then Guy and Chapman came and they told us that it is not exactly like a parallel plate condenser, which means that it is not rigid. Instead, it is a diffuse. It is made of one static layer, and the solution side layer, is actually diffuse layer. So they accounted for decreasing potential with increasing distance from the electrode surface to the bulk of the solution, and also why they show. Also, they explained why the capacitance is not constant. So this model actually addressed this thing. But Guy model has also it also had some demerits. One of the demerits is that it couldn't explain the specific adsorption and freely diffusing analytes interaction. And there are also some other demerits which I cannot recall currently. And then came Stern model, where they combined these two, the Helmholtz model and the Guy-Chapman model. And he proposed that the first layer is rigid, of course, like Helmholtz and Perrin proposed. And then there are subsequent layers with a reduced number of charges, in which the ions are present with their solvation shell, and they are also free to diffuse. And this diffusion rate is affected by convection and thermal agitation. These were the observation from Stern model. And later, there was Bogrees, Mulliken, and Devanathan model, and BMD model. And they proposed that there are some ions which can penetrate the Helmholtz, inner Helmholtz plane, and specifically adsorb to the surface of the electrode directly. And when it does, their solvation shell also will be pushed backward, I mean, towards the solution side. So this is how some electrolyte interact, and the plane that is passing in between them is called, I don't exactly remember that thing. So every model that came afterwards had addressed a new problem that was not addressed by the earlier model. So if you give a short reading to the Wikipedia page, even the Wikipedia page can help you better. Yes. Yeah.
One more question. So I'm working on a corrosion aspect of materials. So let's say if we take example of stainless steel, I imagine a moment where there is a passive layer that has formed on the surface of a stainless steel. Now, two scenarios are there. One, there is still have not formed any passivation layer, and there's another scenario when a passivating layer has formed. Now, I want to understand, now, what is EDL here? What will be the characteristics of EDL is different in both the cases?
Yes.
Is EDL same? Because yes.
Yeah. I could understand your question. If there is no passivation layer, the EDL will be something different, and if there is a passivation layer, the EDL will be something different. And
what changes are we expecting from this behavior?
Yes, it depends on the extent of the growth of your passivation layer. If the passivation layer has covered your stainless steel surface 100%, there will be only one EDL feature you will see in your Bode phase angle plot as well as in your Nikos plot. But if your passive layer is not complete and it has some exposed area of your unpassive stainless steel electrode surface with no passive layer will also have its own EDL, and that is where you see more than one peak in your Bode phase angle plot. That is also a scenario. Yes, that is also a scenario.
Two constants.
Yeah. So when you want to grow 100% covered passivation, I mean a passivation layer with 100% coverage, it should give you a single EDL. So during the growth, you will see more than one. Yes. So you can actually follow using impedance how the passivation layer grows.
Thank you.
Yeah, welcome. So, already 50 minutes gone. Yeah, and there are many in the line, so I'll move on to the next one. Yes, I don't know who came first. Subhash, if you remember, please make one of them as a host.
Mr. Dawali, I think so. He's a host.
Okay. Thank you, Subhash. Yes, Mr. Dawali.
Yeah, hi, Anantharaj. Thank you for your, arranging this nice talk. I'm first time attending your, and I know your research and I'm following you very well. So,
yeah, thank you.
Congratulations for your, nice contribution towards the electrochemistry and OER nature. Currently, I'm in Australia and working in CSIRO as a senior research scientist. But I love your chemistry, very much. Electrochemistry, especially.
Hey, thank you, Dr. Thank you.
Yes. Yeah, this is regarding the electrochemical surface area measurement and then catalyst utilization.
I see your question in the chat box.
Yeah.
Yes.
How do you measure the electrochemical surface area measurement? Because there are many people reporting by the CV or some EIS method, and also by calculating the Baller capacitance, or there are equations they are using, and also how do you come across catalyst utilization, especially if you deal with, like, I know for like a 3-liter system, but if you really work on system level, like 100 centimeter square MIA fabrication and cell assembly and then testing under real condition and production hydrogen, because we always, I'm also from India, so we do HERO reaction and we don't measure hydrogen, oxygen. We always go ahead and just measure potential at 10 milliampere per centimeter square and then report that this is over potential and this is activity, and so, but because of your, I think you are heavily involved. I know you are in Japan now, so I also work in NIMS Japan before, so that's why I'm asking this question. So it will be great if you can elaborate more. Yeah.
Okay. So your question is that you want to calculate
surface area measurements and then catalyst utilization based on that, because we want to know why you want to do surface area measurement, because we want to know how much your catalyst has been utilized, right?
Yes, that is true. Having a dead weight of catalyst in electrode assembly is purely waste of source and time and also money. So I also won't recommend that. So by any chance, have you come across my paper in Angewandte Chemie, the significance of properly reporting turnover frequency?
Yeah, actually I gone through, but it would be great if you can elaborate more here. Just the paper, it's very difficult to understand many things.
Because I have written everything there. So problem with the electrochemical surface area determination is that we cannot do it with 100% precision for all type of material. Even for a single metal containing material like monometallic electrocatalyst, the determination of electrochemical surface area is still a thorn in the flesh. So there is no, I would say there is no single method that can give you the exact value. You may argue that we have under potential depositions, you were stripping for determining the electrochemical surface area of platinum and other similar materials.
Yeah.
But I would say you that even these methods are not accurate.
Yeah, that is the only universal only for platinum. But if you deal with other metals like
Yes.
iridium or ruthenium or
Even
other
with
metals,
even
yeah,
with platinum,
yeah,
if you
people are
change,
reporting different methods. Yeah, UPD and CO stripping and zinc ion deposition. Yeah,
yes, yes, yes. If you take platinum and
yeah,
take UPDS, the method of determining the electrochemical surface area of platinum,
yeah.
if you change the vertex potential of your experiment,
Mhm.
or if you change the scan rate of your experiment, you will
Mhm.
see the EXA will also change.
That's correct.
Yes. So there is no single method that can give us this exact electrochemical surface area value, even for a very simple catalyst like with no complexity, I mean composition wise complexity like
Yeah.
PT. But when it comes to bimetallic or multimetallic catalyst, the problem is even more.
More.
So in that case, what I always suggest is that reduce the loading and see the activity, how it does change. So if you could reproduce the same activity even after reducing the loading by 2 to 3 orders, it means that in your first trial you had some excess catalyst which was just the
Not.
dead weight.
Yeah,
Yes,
not
it was
valid.
released. So to calculate, I mean, coming to your second part of your question, the catalyst utilization technique.
Yeah.
So which is also can be done with electrochemical techniques for monometallic catalysts. For example, 3D iron group metals and platinum, iridium, ruthenium. We can just integrate the charge under the redox peak and we can calculate the number of atom participated. So which can give us uh, an idea about the percentage of catalyst utilization from the loading and the amount of atoms that are getting oxidized or reduced in our reaction. But it is also not an accurate method, just like the HUPD, because it can change with the changing scan rate. So the best way to find out catalyst utilization is that keep reducing the loading and see how it affects the activity.
Performance. Yeah.
Yeah. Yes. So you will now have found threshold loading below which activity will keep on reducing. So that is where your catalyst was able to show its full potential. I mean, in terms of utilization. So there you can get the value of catalyst utilization. Then you can go for any other method I said. If it is a monometallic catalyst like HUPD, CO striping, or redox peak integration. If it is a multimetallic catalyst, you have no other choice other than assuming all your catalyst is participating.
That's correct. But maybe whatever the experience I gain, I can little bit I can talk about this. So
Yes, yes.
what usually you do, because I'm not working on singles like filter system nowadays. I'm
Yeah.
fully
Okay.
working on like 100 centimeters square MIA fabrication, complete, and working on PEM electrolyzer, PEM,
Okay.
not
Okay.
alkaline, PEM.
Yeah. Okay.
So
Okay.
we are, completely. This is like CCM is called CCM, catalyst coated membrane. We're working on that, and
Okay.
we are dealing with like highly expensive metals like platinum and iridium directly. Iridium on anode side, platinum on cathode side, and we are directly printing on membrane.
Okay.
Yeah, and what I usually do to calculate the surface area,
Okay.
because our system is completely sealed, completely black, and continuously we are pushing the water through the system, and we what we do that you mentioned, to know the catalyst utilization, we do CV and then calculate the charge under the CV, uh,
Okay.
like through by again the software, fitting software we use there for CV charge integration, and
Okay.
by knowing the scan rate, and by knowing the your uh, charge under the area, So it's
Yes, yes,
called capacitive, you can say
yes,
charge.
yes,
So I
yes,
calculate
yes.
that one. Based on that, I calculate the,
Yeah,
I
yeah,
know the amount of loading. Already I know
yeah.
the amount of loaded. So based on that, I calculate the specific
Catalyst.
surface
Yes.
area.
Okay,
Specific
okay,
surface area I calculate first. Specific
okay, okay,
from
okay,
the CV.
okay.
But here what I'm doing, because I'm using my platinum is my counter electrode here. I want to
Mm,
calculate suppose surface area of the iridium another
mm,
side.
mm, mm,
And my
mm,
my counter other electrode is platinum. But what I'm doing, I'm back pressurizing that platinum with hydrogen, because hydrogen will be, once I apply the potential, hydrogen is there. So I'm
mm.
completely closing that outlet, and hydrogen will be there. So
Okay,
because we want to use as a platinum as a quasi reference electrode there. There is no
okay.
reference electrode, right? I'm using only two electrode system.
Yes, yes, yes.
So I'm using that system, and I'm pressurizing back, and then my hydrogen platinum will be under hydrogen atmosphere. I'm
Okay,
pushing like 2 or 3 bar, cathode side, and
okay,
scanning under that atmosphere, and I'm calculating, taking the CV. Also,
okay,
I did by impedance as well, but mostly I feel that CV is best instead of impedance, because there are many variations, as you
okay,
mentioned in your
okay, okay,
discussion
okay.
as well. So
Yeah, yeah.
based on that, I calculate the specific surface area by
Mm.
but here the equation of the electrochemical surface area, that is
Yes, yes,
uh,
yes,
charge
yes.
divided by your specific
Capacitance.
like
Ideal divided by specific capacitance.
yeah.
Yes,
So
yes.
based on that, I calculate the specific surface area, and I know the physical surface area from bead
Okay,
surface measurement of your
okay,
catalyst.
okay.
So I just take the ratio of that. I know already physical surface area, and I know the specific surface area of the catalyst under the
Yes.
rail system. So if you
Yeah,
take the just like ratio of this, you will get the catalyst utilization.
yeah, yeah. I agree with that. Yes.
Yeah, that's
Thank
what
you
I
very much.
do for full
Yeah,
full
yeah. That's
scale
something
system,
new
and not
I learned.
for half cell.
Yes.
Yeah,
Okay,
that may be
okay.
not applicable to for half cell, but
Yes.
people may can try. And
Yeah, yeah,
this is because
yeah.
there is one paper from US professor. He
Oh,
has
okay,
done some work on that,
okay.
especially like people who's working on OER, OER, and they are
Mm.
using some iridium or some iridium ruthenium or ruthenium.
Okay.
They
For
can
for
refer
that.
that paper. Yeah,
Yeah, yeah. Thank you, Dr.
so,
Dawal. Yeah,
yeah.
yeah. It's very useful. Thank you very much.
Yeah,
Yes.
thank you
So,
for your
yeah.
information as well. Yeah, definitely I will contribute such discussion. I love such
Yes,
discussion.
yes, yes. We would love to have. Yeah.
Yeah,
Thank you very much, Dr. Dawal. Yes, yes.
yeah.
Yeah. The next one. Oh, there are so many questions in the comment box. Yeah.
Sir, are you listening? I am speaking Palani from my area.
Yeah, yeah, yeah. Please.
Sir, actually, suppose we have some carbon different morphology with the
Mm-hmm.
low cost elements, for example, irons and other. We can improve the catalytic property because supporting carbon microstructure acts as a freely moving the uh, electron, as well as we can reduce the cost also instead of using iridium and palladium platinum.
Yes,
That's
yes,
why we
yes.
are thinking,
Yeah,
is it possible to?
yeah, I get your question. Yes, the main objective of using non-noble metal is to replace noble metal. In my opinion, which is impossible because we cannot completely avoid the use of noble metals. But non-noble metals, even though it is cheaper, they cannot be as stable as noble metals, and they cannot perform the same catalytic reaction as well as the noble metals. Using carbon can give us a few advantages, like
Okay.
improved conductivity, better charge transfer, and also if your catalytic reaction is not involved in potential where the carbon corrosion occurs, it can also add up more stability. But if you are working with water electrolyzer, for example, so it is not a good idea, I would say. So
Okay.
because carbon corrosion is inevitable if you are particularly using your catalyst for OER. So
Okay.
after some time, obviously all the carbon, whatever you have as a microstructure, which is originally intended to improve your catalytic activity, will be corroded completely.
Okay.
So that is, yeah.
Oh, yes, sir. Yes, sir. So if you look at it, the carbon microstructure and the water electrocatalysis, because for example, there is no any ion for deionized water. Then there is no aggressive ions in the water. Then microstructure won't to be affected easily. Then even though in the pure water, my carbon microstructure also not affected and the corrosion also not occur as much as long time we are using as a catalyst. This is the we are thinking to do, but that's why I just think I discuss.
But the problem is your deionized pure water is highly resistive.
Okay. Yes.
So you know the resistance, right? 18.2 mega ohm. Yes, I think 18.2 mega ohm, which is way too resistive.
18 C1 micro C1.
Yeah. Yes, which means that it is virtually non-conductive. So when your solution is non-conductive, it is meaningless to have a stable electrode. You will have to apply huge potential in order to affect the electrolyze. So that is why people always use some sort of salt or acid or alkali to split water, because pure water is a resistor, not a conductor. So you need to have alkali or acid or some sort of salt to perform water electrolysis. Otherwise, it is not possible. I agree that having a deionized water will not affect your microstructure, and also it will not lead to carbon corrosion, because even though you are going to apply the potential which is said to be causing the carbon corrosion, because of the resistivity, increased resistivity of the pure water, reaction will not occur, so that the carbon corrosion may not happen. But your end objective, I mean splitting water, will not be possible with pure water. Yes.
Yes, sir. We can some sort of sodium bisulfate for conductive purpose. We are taught to use sodium.
Yes. Yeah. When you do that, you will obviously have to go to the potential where carbon corrosion occurs. It doesn't matter whether you have alkali or acid or neutral salt. So when you reach that potential, if your solution is conductive enough, the carbon corrosion is unavoidable.
Okay.
Yes. Yes.
Okay. Thank you, sir. Thank you.
Welcome, Mr. Polani. Yes. And
Hello, sir.
Anuj Kumar. Yes. Oh, Jagadish. Oh, yeah. Jagadish has been. Yeah. Please.
Yes, I have some basic questions.
Yeah.
As during a CV measurement, and when I increase the scan rate, the more than 100, the continuity of the CV graph is missing. What is the basic mean?
I don't get what do you mean by continuity.
The graph is not completed. The redox phase or oxidation reduction phase is not completed. When I increase the more than 100, 200, 300 milliwatt per second, the continuity of the CV graph is missing. And the flow of conductivity is not missing. It's not completed.
So if you have some graph, can you show? I really don't get what you mean by continuity. So is it not the exact redox peak?
Yeah, when the starting and the ending peak is not completed. So where is the start peak and the in between the conductivity is missing in between the electrode and the redox and the oxidation.
Jagadish, I'm very sorry. I couldn't picture what you are saying. So if you have the graph with you, please show me. I will try to help you. I understand that when you increase scan rate, your redox peak are missing. Am I right?
Redox, not only redox, the continuity
so unless you show me your cyclic voltammogram, I couldn't help you with this. I'm very sorry. So
I don't have. And one more question, sir. The platinum electrode will get corroded due to the over potential.
So that depends on
the pure platinum
direction. Yeah, direction. I mean, if it is cathodic, it won't. If it is anodic, it will for sure.
Okay.
Yeah.
So, and
If you
one more question.
yeah.
And during electrode preparation, the thickness of the electrode is important. Important or not?
Yes,
When
absolutely.
yeah.
Yes,
So,
it's very important.
I
Very, very
am working. I am working supercapacitor application. The
Yeah.
supercapacitor only for the surface interaction.
Yeah.
But in this case, the electrode, the thickness of the electrode is important.
Yes, it is important. The electrode thickness is directly proportional to interfacial resistance. When the resistance increases, the charging of your capacitor and discharging of your capacitor will also be very difficult. So obviously your capacitance will get affected. So you need to optimize the thickness of your electrode in order to have an optimal resistance, because the capacitor works in all circuit. The capacitor has to be charged through the resistor. When you have high resistance, obviously the time taken for charging and discharging and the amount of charge accumulated as capacitance will also be very low. So resistance must be lowered.
Okay, thank you so much.
And then Dr. Mahesh, please go.
Hello, sir.
Yes.
Hello, sir.
Yes.
I am following long back you. Like continuously, I am following your lecture. Thank you,
Thank you
sir.
very
You
much.
are giving many suggestion, good suggestion. So I
Yeah,
am
thank you.
also like electrochemistry background. So
Okay.
right now I am in Engdam University, South Korea, doing a postdoctoral fellow.
Okay, nice to know that.
Uh, so here, sir, I done some HER and OER work. There I
Yeah.
did some impedance studies, sir.
Hmm.
But normally I fitted after getting the impedance spectra. I got only two resistance: solution resistance and charge transfer resistance.
Hmm.
And CDL also I got. But some paper like your paper and review paper I am following, they're also telling product resistance also it will come. Generally, how many resistance it will come to OER or HER, sir, in impedance?
So product resistance is a concept where the product stays at the electrodes interface.
Okay.
Right. So when A is converted into B and B is not moving away or not escaping out of the solution, it accumulates on the surface of the interface. Right. So that accumulation of the product will impede the diffusion of the active analyte, A, reaching the surface. So this adds up some resistance. This is what is called the product resistance. But in our case, it is HER and OER. So in both cases, hydrogen and oxygen escapes the solution. So the interface is always free for the incoming water molecule to approach the interface. So you don't have to worry about product resistance in case of
Product
HER.
resistance.
Yeah. So not only HER, OER, any gas evolution reaction. Yes.
Okay.
Yes.
Thank you, sir. Thank you.
Yeah. Welcome, Dr. Mahesh. Yes.
Thank you.
How DFT useful in understanding catalysis and any suggestion to use catalysis research? Yeah, DFT is it has now become one of an integrated study, because so far people have been designing catalyst and performing electrochemical analysis and saying that this after this kind of optimization perform this much, but there is no true insight why it does so. So that's where the DFT comes into the picture. So in DFT, what people do is that they construct the models of our catalyst surface based on the data what we give to the DFT team from the physical characterization. They will construct the lattices, maybe slabs of the surface, atomic or molecular slabs of the surface, and they perform energy of interaction of the intermediates involved in the reactions what we are studying. So our reaction, for example, if you take hydrogen evolution reaction, so there is water dissociation and hydrogen adsorption, electrochemical discharge of adsorbed hydrogen, and then evolution of hydrogen. All these reactions are simulated theoretically, and the energy of interaction of all these intermediate steps are studied in DFT. So obviously the intermediate step which is going to be having highly positive or unfavorable, I mean unfavoring energy of interaction will be the one, the rate determining intermediate step. So your best catalyst obviously should have the free energy closer to zero or in the negative value. So usually it is not negative for electrocatalytic reactions such as OER, because some amount of energy has to be applied in order to perform this reaction, because it is a non-spontaneous reaction. So you need to look for energy of interactions of each intermediate step and find out which step is having the highest energy of interaction, because that will be, I mean, highly positive energy of interaction. That will be your rate determining step, and compare the rate determining steps free energy change with all the other materials you are studying in your study. So that will give you an idea why your material, optimized material, is highly active, because it requires less energy, or it has favorable energy of interaction in the rate determining step of the reaction. So that's how DFT has been so far used in catalysis research. Yeah, Anushka, please give some suggestion for my query. I think I skipped it. You skipped it. Oh, yeah. Sorry, Mr. Anish Kumar. I see your question now. How do we know the active metal in the OER catalyst when we have more than one metal? That's a very good question, and that has been a topic of debate for a very long time. Because even for a simple material like NaFe oxide, nickel iron oxide. Some says it is iron, some says it is nickel, and they are all coming up with various experimental proofs. If you have time, please go and read the review I have recently published in Nano Energy. The title is the FE effect. Uh, I forgot the remainder of the title. So where I have discussed all the results that supported that Fe is the active site, and I also discussed the results that supported the nickel is the active site. So it depends on the perspective in which we see the result mostly. That is what I understood. If you take only iron, and if there is no other metal, it is a poor catalyst for OER. If you take only nickel, it is a moderate catalyst. But when you combine these two, it becomes a superior catalyst. So it is usually the synergy between these two. They support one another, in which they lack when they are alone. So iron oxide hydroxide, despite being a very good OER catalyst, needs a conductive host, electronically conductive host, which is fulfilled by nickel oxide hydroxide. Nickel hydroxide and nickel oxide hydroxide is a moderate catalyst and also highly electronically conductive, but it has high, I mean, high oxygen bond strength. Nickel oxygen bond strength is stronger than iron oxygen. It needs some push by having an adjacent Fe site, which by converting into Fe4 oxidation state can help moderating the oxygen binding energy. So that's how they help each other, and they together become superior catalysts. So in any case of bimetallic or multimetallic catalyst, if you see some sort of enhancement, it should be because of two reasons. One is the intrinsic synergistic enhancement. Secondly, this is the most common cause. Where we have more than one type of metal, we obviously have more than one type of more number of active sites. So that causes the enhancement. So you can actually distinguish this enhancement by comparatively studying CDL and electrochemical impedance, which I have explained in my paper published in Journal of Electroanalytical Chemistry. The title of the paper is "Why Shouldn't Double Layer Capacitance Should Be Trusted in Justifying the Activity Trends of Faraday Reactions." I don't know the exact title is this or not, but this is something similar to that. So that's how we say whether the activity enhancement because of having more than one metal comes because of the intrinsic synergistic enhancement, or because of having more number of catalytically active sites. So it could be extensive or intrinsic. We don't know until we study both CDL and electrochemical impedance spectroscopic result comparatively. So instead of arguing which is active set and which is not, we should actually look for how they are assisting each other in enhancing the activity. So that will be the more rational question to ask. Yes. So if you have time, please read the 2 papers I have mentioned. I hope you will find it interesting. So we go how the materials are chosen for NEHR, OER, or CO2 reduction. Yeah, the answer is very simple. Read all the recent reviews. You will get it. Yes, that's very, very simple. I have been receiving questions like this, that what materials will work for OER, HR, how material is decided. So any reaction, simple thing is that your material, according to Sabatier principle, or Sabatier Balkan, we have seen many plots. Your material should not bind with your intermediates, the reaction intermediates, either too strongly or too weakly. So it should be moderate. The energy of interaction should be optimal. It should not be weak. It should not be strong. So both the cases, the reaction will be limited by this unfavorable nature of energies of interaction. So there are only a few metals and metal sites which have such optimal energies of interaction for particular reactions. For example, nickel and 3D ion group metals, Ru, iridium, all these things are having such an optimal energies of interaction towards the intermediates involved in oxygen evolution reaction. So if you are working in CO2 reduction, these things are written in almost every review. So if you are willing to work on any of this area, please go to Google Scholar and download some recent reviews and read them. So if you read 2 to 3 reviews, you will become a master. You will not be asking questions like this to me or anyone. So you will be answering other people. Yes, thank you. And there is, thank you, welcome. Surface Jagdish, group elements of the layered material will decrease the capacitance value. I'm not sure. Surface group elements. Mr. Jagdish, I do not understand what you mean by surface group elements.
Hello, sir.
Yeah.
So nowadays the favorite method, the MX in 2D materials, to have a surface element, fluorine, OH groups and all. In this surface group, when I increase the higher figures, the capacitance values decrease. I last see the one review article. So they mentioned the surface group elements to decrease the capacitance value.
Okay, that might be something. Surface group elements could have become redox active, or could have ruptured the layered structure, and it would have decreased its surface area, so that the double layer size also decreased, and it could affect the capacitance value. But I am not sure how could it. Yes, I'm not sure. I'm sorry.
Okay. Thank you.
Yes. Pitan Pratihar. I have a. At what potential shall we conduct EAS when comparing the charge transfer resistance of electrocatalyst for OER? Yes, excellent question. So there have been so many confusion around this particular question. Some people conduct at onset potential, at a potential of 0 versus reference electrode, at a potential of 0 against the OCV, or at OCV. Some people set a potential just before the onset potential, and some people set just after the onset potential. I have taken this problem very seriously a couple of years ago. I published a paper in Chem Electrochem. The title of that paper is Appropriate Use of Electrochemical Impedance Spectroscopy in Electrochemical Water Splitting. So if you read that paper, you will see that at the end, I have suggested to set potential in the catalytic turnover conditions, not at onset or before onset, or at redox peak of the catalyst, or at the 0 volt, or at OCV. but in the region where your catalyst is actually delivering the catalytic current. That is where you should set your electrochemical impedance spectroscopy's potential, set potential. And I also suggested to do more than one experiment, not at a single potential measurement. If you are studying 4 catalysts together, in which one of your catalysts is well optimized to do the reaction in a better way, you need to choose a range of potential and perform electrochemical impedance analysis and compare the RCT, phase angle, and other parameters, whatever you get from impedance analysis, and see how this trend changes, and compare this trend with the activity trend, whatever you see with the LSV or the CV. So that's how it should be performed. That's my daughter. Yes. Sai Prasad Nayak, the conversion of current to current density can be done using EXA or geometric area. What is correct? That depends. That depends. So if you are very much worried about your real surface area, okay, if we know that there is no ideally smooth surface, and any geometrical area, whatever we think we know, is not the real surface area. So the activity varies with the surface roughness, which means that the surface roughness, increasing surface roughness, increases the real surface area or electrochemical surface area. So normalizing the activity with the electrochemical surface area is actually the correct way. It should be the correct way. But the problem is that we don't have any reliable method to determine the electrochemical surface area to do that. So that's where we are lacking still. So that is where we are given with the only option of normalizing geometrical area. But with all the advancement that have been recently made, wherever you have chances and the ability to conduct electrochemical surface area measurement precisely, I always advise all my peers and followers to do the normalization using electrochemical surface area. Yes. Yeah, thank you, Mr. Pradhan. Yeah, thank you. Yes, we have 6 more minutes for today's session. And one more thing, because it has been so long since we met last time, the questions have piled up in my inbox. So I would like to conduct this session hereafter once in a month, because it was every week previously. And I found that not everyone who registered for the discussion have not were not interested in coming for the discussion. So I decided to conduct this discussion series thrice in a year. But I also find that difficult because all of you do not get the chance to ask or discuss the things that you want to discuss with me. So it will be hereafter once in a month. So we will meet every second Saturday of a month. I will update this information in my website, and I will also share it on the social media platforms. And if you have any final question, I have 5 more minutes I can answer, or we can conclude the meeting with this today.
Hello, sir.
Yes, Dr. Mahesh.
Yes. Just you were just a 2 minute back. You were talking about ECSA.
Yeah.
Which potential we have to do ECSA? Because normally I saw many papers. They are doing OER or HER ECSA, where it will start onset. Before that, they're going to take that potential. They're going to take different scan rate. According to that scan rate, they're going to plot. That is the one correct one, right?
Yes, that is the CDL method. So it is not necessarily to be before the onset potential. Okay, what you can do is that you can perform a full CV covering both OER and HER onset potential, and plot the full CV where you can see the non-ferritic region, truly non-ferritic region, free from all sort of ferritic other parasitic reaction. I would say catalyst-oriented side reactions like catalyst oxidation and reduction reaction. This thing can also affect if you choose a potential region which is closer to your onset potential. For example, if you have nickel hydroxide, nickel as your catalyst for OER, So there is a nickel oxidation peak. You cannot choose that potential for performing.
Yes, exactly.
Yes. So in that case, you need to perform a full CV. In that full CV, you can identify where the real non-Faradaic region is. So you can perform the scan rate dependent CDL measurement there, and then if you know the specific capacitance, or if you could determine the specific capacitance for your material, you can calculate the electrochemical surface area. Yes.
Okay.
Yeah. Can you suggest any books related to electrochemical analysis for beginners? I started reading the Electrochemical Methods, Fundamentals and Application by Bard and co-authors as a beginner. I also suggest the same to everyone. If you find it too difficult to understand, please read any standard chemistry textbook, physical chemistry textbook. So if you could grasp everything in the electrochemistry units given in those physical chemistry textbook, it will not be difficult to understand the electrochemical methods, fundamentals and applications written by Professor Bard. Yes. So using XPS, we can find out electron transfer between multimetallic catalyst, which will confirm enrichment of some metal site and help understanding metal is more active. Is this method correct? I have never heard this method, but I will definitely do some research about this. And when we get back next month, I will definitely answer this question. Thank you. This session will be uploaded on YouTube. Yes, definitely. Can we calculate the TOF from equation which you provided in the article, precision correctness for the GC modified electrode? Of course you can. Yeah. Yes, Ms. Bhagyashree Kamble. Yes, you can do that. Yeah, it's almost time and I'm exhausted from talking for more than 90 minutes now. So I think it's enough. Thank you guys for having joined me today. I'm looking forward to see you all again next month. I'll share you a unique meeting ID link. We'll meet again. Thank you all for being here today. Yeah. Good night.
Thank you, sir.
Yeah, thank you.